in order to approximate the arc length of the curve in blue, well, I will need to add up the lengths of the individual line segments, and that shouldn't be too bad. All I need is a little bit of geometry. Well, here we see what would happen as I take more and more of these line segments. My approximation gets better and better. But we've been expecting that for a while now. That's starting to become part of the intuition. That's what I would diagnose as calculus brain. And we want that. We want calculus brain. I need to find the length of those individual line segments. So what am I going to use here? I'm going to use geometry. So the length of each of these line segments is going to be the hypotenuse of some triangle. Hypotenuse of a triangle is the square root of the square of the base plus the square of the height. The base is going to be my delta x. And fortunately enough, that's going to be the same for every single one of these intervals. The height is what could change, and I will call that delta y sub I. So depending on which interval I'm at, I could have a very steep triangle, I could have a very shallow triangle. It'll depend on what the value of I is. But all this delta notation is saying is we take the value of the function at the right endpoint, call that yi, and we subtract off the value of the function at the left endpoint, call that yi minus 1. Okay, so each of those individual lengths has the formula the square root of delta x squared plus delta y squared. Now, what gets me back to integrals and what gets me back to calculus? Well, one way you can look about it is with the mean value theorem. So those delta y's I could also call f of xi minus f of xi minus 1. And if this function is differentiable, then the mean value theorem tells me that there's some test point, maybe I'll call it x star, so that the derivative of the function at exactly the coordinate x star solves this equation. Delta y equals my derivative times delta x. Does that allow me to simplify the formula? Why, yes, it does. So what is going on here? I can rewrite so that my delta y is really the derivative of my function times delta x. Both of these quantities have an a delta x squared in them. I'm going to factor that out. And if I have the square root of delta x squared, why, that must be delta x. Okay, so my Riemann sum looks like this. The summation I goes from 1 up to n. My summand is the square root of 1 plus f prime of x star squared, all times delta x. And we know what happens to Riemann sums when we take limits. All of my big chunky Greek letters turn into nice smooth Latin letters. And I've got the integral from a to b of the square root of 1 plus f prime of x squared, all dx.